Hello students, I am Dr. Kulvinder Singh. Today we are taking some of the numericals from the special theory of relativity. But before we actually go to the special theory of relativity, let us try to understand what is the meaning of the relativity. Whenever we observe a motion, it is quite important to know the frame of reference through which the motion is observed. Say for example, I have a frame of reference which is the S frame of reference, and there is another frame of reference which I have shown by the dotted line, that is the S dash frame. They initially are coinciding with each other. That means their axis X, Y, Z axis, they are also coinciding, origin also is coinciding, but that is a story at time t equals to 0. But frame S is in rest position, this is in rest position, but the frame S dash has a uniform velocity Vf. That means the velocity of this frame remains constant with time. That's why we call these frame as inertial frame of references, right? So if this frame is in motion, then obviously after some time they get separated and situation will be something like this. The S frame which was in rest will remain there, but S dash frame obviously will move to some position. Let me call the observer of this frame O dash and the observer of the frame S as O. So this distance is covered by the frame, and that obviously is equals to Vf into t. Now if the velocity involved are very small as compared to the velocity of light, then we can easily use Galilean transformation equation. Now in this case, we make some assumptions, and these assumptions are like this, that we assume that in this particular case there is no variation of the time interval. There is no variation of the mass also. It means whenever we make an observation for a particle, its mass remains as seen from the S dash frame of reference. Similarly, if there is a time interval measured by the observer O and time interval measured by the observer O dash, they are exactly equal. These are the simplifications. Later on we'll see in Lorentz transformation equation, they are not going to be constant. But this is only possible when the velocity involved are very, very small as compared to the velocity of light. Now, if I have a particle somewhere as P, from this observer, the position of the particle is given as R dash, but the position of the particle from S frame is R vector. So obviously we can connect R dash vector as R vector minus Vf into t. That means if I have to move from here to the point P, I will go back first of all to O, covering this Vft in the opposite direction and then R in the positive direction. If I differentiate to get the velocity, that is V R dash over dt, we are going to get the velocity V minus the velocity Vf. In this case, I have not taken t dash. Notice this point. It means we are taking the time interval to be same, both in S frame as well as in S dash frame. Now if you further go for the acceleration of the particle, this comes out to be A dash. So equation 1, equation 2 and equation 3, these are the three important transformation equation for the motion of the particle when you have to move from a stationary frame to a moving frame. For simplicity, what we do is we take the S dash frame moving only along the x-axis. Say is going along x-axis only. Say with the velocity v, f. There's no need to put a vector because we already have made the statement that this is going in the x direction. This is my frame S and this is moving along the x-axis. Now these equations can further be simplified in terms of the coordinates as x dash is equals to x minus vf into t, y dash will remain as it is, z dash will remain as it is. Reason being, this motion is purely along the x-axis. Further, if I go for the velocity, this is v dash along x-axis, let me call this as vx dash. This is going to be vx minus vf. Here it is very important to note down that these are the velocities of the particle and vf is the velocity of the frame. Right? This must be very, very clear to you. And if you go for the y component of the velocity, it is going to be same. Similarly, z component is also going to be same. Since our frame velocity remains constant, if I further differentiate to get the acceleration, we find that the acceleration along x-axis is same as the acceleration along x-axis in S frame. Similarly, y component as well as the z component. So these are the transformation equations for a simplified situation where the moving frame is along the x-axis. So you please take care of this while doing the numericals, whether it is a generalized thing given to you or a specific thing where the moving frame is moving along the x-axis. Now let's take the second point, and this is famous Michelson-Morley experiment. There was a time when it was believed that light travels through a medium which is named as luminiferous ether. It is assumed to be in the rest position in space, and every other thing, including the earth, stars and everything in the universe, is supposed to be moving in this frame. Now if we talk about the orbital velocity of Earth around Sun, this means that from Earth we'll find the luminiferous ether is moving in one particular direction. This experiment was actually aimed to find out whether this luminiferous ether exists or there is no such luminiferous ether. Although the result came out that there is no luminiferous ether, but let's quickly understand the experimental setup of this Michelson-Morley experiment. We have a monochromatic source, say a wavelength lambda. With the help of a lens, we make a parallel beam which we allow to fall on a glass plate which is half silvered from the back and is kept at an angle of 45 degrees. The light which is going towards it get reflected from the surface, lower surface, as well as there is a part which get transmitted. Now the part which is reflected comes out from it and moves towards the plane mirror M1 kept at an angle of 90 degrees. The light which get refracted has to pass through a compensating plate P2 and then reaches to a plane mirror M2 and get reflected from there and meets at this particular point. Say, let me call this point as P. They get separated from here and they again come and meet at this particular point. But they travel in a different direction. Obviously, if there is a luminiferous ether, as if the whole luminiferous ether is moving, suppose we have the Earth movement in this direction, so obviously the luminiferous ether is assumed to be moving in the opposite direction like this. So obviously the light which is traveling perpendicular to this flow will return to the point P traveling a different time, and one which is going towards the mirror M2 is reaching here at the point P traveling a different time. So definitely there is a time interval between the two. The one which is going in a perpendicular direction, this takes the time t1 equals to 2d by c under root of 1 minus u square by c square, where d is the one side distance between the point P and the mirror M1, and we assume that exactly the same distance is there for the M2, and the time when the light travels parallel to the flow towards the mirror M2 is given as 2d by c under root of 1 minus u square by c square. Here we should note that u is the orbital velocity of Earth. The orbital velocity of Earth is nearly 3 into 10 to the power 4 meter per second around Sun, and velocity of light, as we know, is 3 into 10 to the power 8 meter per second. Obviously, this velocity is not comparable to the velocity of light. It is quite small. So assuming u to be small as compared to c and making simplification, we get the time interval as du square divided by c cube. It means the time taken by these lights, which are going one towards M1 and other towards M2, when they meet, they have time interval of this value. So obviously there is a path difference, and path difference can simply be obtained by simply multiplying it with c, and that is equals to du square by c square. This is equation number 1, is equation number 2. Now what Michelson-Morley did, they rotated the whole setup by 90 degree. What happens because of this? The light which is traveling perpendicular to the flow of the luminiferous ether now will start going in the parallel direction, and the one which is going in a parallel direction now will start going in a perpendicular direction. So there must also be the path difference, but obviously this time it is going to be negative of this. So if you get the total path difference, this is the total path difference after rotation, so that will be equals to du square by c square minus of minus du square by c square, and that is equals to 2d u square by c square. So this is the total path difference which we observe when we rotate the whole of the setup by 90 degree. If we are looking for the maxima of this interference, then the maxima of the interference will change the, or you can say the shift in the number will be given by 2d u square c square into lambda divided by lambda, because L lambda is the condition for the maxima, so lambda comes in the denominator. So this is going to be the number of the fringes that they get shifted if there is a luminiferous ether. And as we all know that they conducted this experiment at various places in many different situations, but they couldn't find that even a smallest change in the number of fringes, though their apparatus was designed to detect even the 1/100th of the fringe shift, but they couldn't get any such shift, and finally they concluded that there is no luminiferous ether. As a consequence of Michelson-Morley experiment, which proved that there is no luminiferous ether, Albert Einstein gave two postulates for special theory of relativity. One of them is that all laws of physics, they have the same form in any inertial frame irrespective of the velocity of the frame. This is the first postulate. The second postulate is that the velocity of light observed by the observer of any inertial frame moving in any direction always remains same. We assume here that there is no medium and light travels in vacuum. So if light travels in vacuum, the velocity is very close to 3 into 10 to the power 8 meter per second. This velocity always is observed exactly of the same value, whatever may be the inertial frame of reference. So students, as a consequence of Michelson-Morley experiment, Albert Einstein gave the special theory of relativity with two postulates. Now when we say the velocity of light remains constant in both the frames, one thing is quite clear, that the Galilean transformation equations are no more valid now. Because in that case we have the transformation equation for velocity also. But when we talk about the velocity of light, postulate says it's same. So we need another set of transformation equation which was provided by Lorentz and known by his name Lorentz transformation equation. Here we have again two frames. One is S frame and another is S dash frame. S frame remains in the rest position, whereas S dash frame is moving with the velocity v along the x-axis, and this remains constant, which makes both S and S dash inertial frame of reference. Let's talk about an event observed by the observer of the S frame as x, y, z, the position coordinates, and at time t, whereas the observer of the S dash frame says that this occurs at x dash, y dash, z dash, and at time t dash. So if we are given the information for x, y, z and t, and we are looking for what are the values for x dash, y dash, z dash and t dash, we call these transformation equations as direct transformation equation. And this is x dash is equals to x minus vt divided by under root of 1 minus v square by c square. Whereas y dash remains y and z dash also remain z. This is obvious because our frame is moving only along the x-axis. There is no movement along the y and z axis. That's why these coordinates, they remain as it is. However, there is a transformation equation for time, and that is t minus v x divided by c square whole divided by under root of v square by c square. Now this means that we know the parameters from the S frame and we are finding out the parameters in the S dash frame. If we do the reverse of it, it means that now my observer is in the S dash frame. So obviously, if I am in the S dash frame, I will find the S is no more in rest position, but going in the opposite direction with the velocity minus v, right? So this minus v will change these equations, and your inverse transformation equations now will be x equals to x dash plus vt. There will be no change here in the denominator, as minus v whole square will give you the same. So this component will remain as it is. Once again, y is equals to y dash and z is equals to z dash, but there is a change in the time, and t now will be equals to t dash plus x dash v divided by c square under root of 1 minus v square by c square. So these are the transformation equation for position and time, and we call them as the Lorentz transformation equation, although we can derive for velocity and acceleration, which we'll see later on. But these are the basic physical quantities, that is the position and time. For these we have the transformation equation. This factor 1 by under root of 1 minus v square by c square is sometimes called, this is a constant, it's called Lorentz constant, because once the velocity of the frame is fixed, so this remains constant, so you can evaluate it separately and you can keep on putting it in the equation wherever is required. The second interesting thing is that if we assume that the velocity of the frame is very small as compared to the velocity of light, look, this factor will go, v square by c square factor will go, and we finally reach to the Galilean transformation equation. So please keep it in mind that Galilean transformation equations are not wrong, but can only be applied when the velocity of the moving frame is very small as compared to the velocity of light. But if the velocity becomes comparable, then you have to use the Lorentz transformation equation. So you can say Galilean transformation equations can be obtained from the Lorentz transformation equation under this situation. So students, we have seen that in Lorentz transformation equation, even the time is not invariant. Time is invariant in Galilean transformation equation, but not in the Lorentz transformation equation. There is a different way to look at it, and we call it as a space-time coordinate system. Although when we talk about the space coordinates, we normally represent it by this, saying that this is x-axis, this is y-axis, this is z-axis, and all are perpendicular to each other, so that they are independent of each other. But to think of the fourth dimension, independent of all the three, it is not possible to give a shape in three-dimensional space. So we have to keep it in mind. Let's look at this in this simple way. Let me take this axis representing the space coordinate or the space vector, whereas this represents the time. Normally this is given as I cap ct. C is the velocity of light, t is the time, and I is iota, which is -1 under root. This helps the thing later on when we do mathematics of it. So these two are the axes, and keeping them at 90 degree means that we are keeping them independent of each other. So if there is an event somewhere in this space-time coordinate system, its distance from the origin, let me call this distance as s, will be given as s square is equals to r square minus c square t square. Obviously, because r and ICT, they are the defining coordinates of this particular event. So this is the distance from the original. Now you can think of a more modified version of it, that suppose at present state we are here at this particular position, and here we have some event. So if we look for all possibilities of time, so you can make this length to rotate and forming a cone, but since it is a time beyond the present, we call it as a future cone, future time cone. And obviously its image on the negative side of time is the past time, and this origin belongs to the present time, and this hypersurface is a present status. So we can think of the past, present and future, right? This is the advantage of this type of a system. But here is very important to note down, there are two important properties. If you are observing this space time distance, that is s, from any inertial frame, you will find this s square, or s you can say, is Lorentz invariant. invariant. Moreover, if you take a 4-dimensional volume which can be given as dx, dy, dz and dt, this also is the Lorentz invariant. So this is the advantage of the space-time coordinate system. It helps you to visualize it in a more easier way. But there are certain conditions to remember. If you find that s square is less than 0, that means it is imaginary s, or s square is less than 0, we call it as a time-like interval. This is time-like interval. Or if you have s square greater than 0, that means this is real, we call it as a space-like interval. Or if you have s square equals to 0, we call it as a light-like interval. So you can classify any interval given to you, whether it is a time-like, space-like or light-like, with the help of these things. So as a result of Lorentz transformation equation, there are two interesting effects we have. One is length contraction. Suppose we have this frame which is the S frame and is in the rest position, and this is a frame which is moving along the x-axis with the velocity v. There is a rod lying in the S dash frame and is moving along with the S dash frame. Let's say its original length is O. When we say its original length, it means the observer who is observing this rod is also moving in the frame S dash. That means observer and the rod both are moving with the same velocity. That means they are relatively in rest position. But the observer of this frame S, if he can see this rod, he will notice that the length is equals to L0 under root of 1 minus v square by c square. Obviously L is less than L0, that's why we say it's the length contraction. There is another effect which is called time dilation. Once again we have this frame S in rest position and this frame S dash is moving with the velocity v. Now suppose there is a position x dash where two events occur. According to this observer, the timings are t1 dash and t2 dash. When I put a dash here, it means I'm talking about the observation made by the observer who is moving along with the S dash frame. For him, the time interval, which is the original time interval, is t2 dash minus t1 dash. But once again, if the observer of the frame S is observing the two events, for him the time is equals to original time divided by under root of 1 minus v square by c square. So we can see from here, since delta t is greater than that of original time interval, we call it as a time dilation. Now let's take the transformation for the velocity and acceleration. Once again we are taking the S frame in the rest position and S dash frame is moving with the velocity v. Now in this frame, let's say there is a particle which appears to this observer O dash, moving with velocity v dash vector, having an acceleration of a dash vector. Now to this person who is in the frame S, says that the velocity is v vector and acceleration is a vector. You can say like this, the velocity has the coordinates vx, vy, vz, acceleration as ax, ay, az for the observer of S frame, and similarly vx dash, vy dash, vz dash are the coordinates of the velocity observed from the S dash frame, and the acceleration coordinates are ax dash, ay dash, az dash. Now we are taking a factor which is very commonly is used, that is a Lorentz factor, 1 by under root of 1 minus v square by c square, and we are representing it by gamma. So these are the direct transformation equation, and these are the inverse transformation equation for velocity. And similarly we have the transformation equation for acceleration. You please pause the video and take the screenshot, because these relations are very complicated, so one has to practice it by writing it 2 or 3 times so that you can use while doing the numericals directly. Students, we have seen that there are transformation equations for the velocity, acceleration, but as per the postulate of special theory of relativity, all laws have the same form in all inertial frame of reference. Say for example the law of conservation of linear momentum. So if we take that into account, we come to a very interesting result, and that is the relativistic mass concept. That is the relativistic mass concept. A particle in rest position has, say, the mass m0, but when it is observed while moving with the velocity v, its mass appear to be m0 under root of 1 minus v square by c square. So if you plot this mass versus the velocity, you will get a very interesting result, that there is a continuous increase in the mass of the body. This is essentially required in order to have the conservation of linear momentum, say for example in a collision experiment. Further, we have a concept of relativistic energy. This is given as E equals to mc square, where m is the relativistic mass. Now further, we have another relation which you can remember easily from the Pythagorean pair like this. Say this is P into C, where P is the linear momentum of the body and this is m0 c square. So this hypotenuse will be mc square. So using the Pythagorean pair, we can write mc square whole square must be equals to m0 c square whole square plus pc whole square. So this will help us to get the energy. This is the rest mass energy concept, and this is basically is the kinetic energy concept of the particle. So students, let's see the transformation equation for the momentum and the relativistic energy. As usual, we have a frame in the rest state. With respect to this, there is another inertial frame S dash which is moving along the x-axis with the velocity v. Now the observer of S dash frame observes that a particle is moving and has a momentum component as px dash, py dash and pz dash, and its relativistic energy is E dash. Now to this observer who is in the frame S, the components are Px, Py, Pz and relativistic energy is E. Taking the Lorentz factor as 1 by under root of 1 minus v square by c square, we have these transformation equations for momentum and energy. There is no transformation required for the y component of momentum and z component of momentum, as the frame is moving purely along the x-axis. And these are the inverse transformation equations. So students, let's take now the Doppler effect. The Doppler effect in light is different from the Doppler effect in sound. In sound case, when we have observer and source, they are in motion, it depends who is moving, observer or the source. But in Doppler effect in light, it doesn't matter, we only look at the relativistic velocities. There are two types of the Doppler effects. One is called the longitudinal Doppler effect. When you have a source and observer, they are moving on a line joining them. We call it as a longitudinal Doppler effect. The frequency, apparent frequency observed to the observer is the real frequency nu multiplied by 1 minus v by c, 1 plus v by c, where v is the relative velocity. This relative velocity is negative if they are approaching each other. But if they are going away from each other, then we take the relative velocity to be positive, going away from each other. Similarly, when we have the movement of the source or maybe the observer in a direction perpendicular to the line joining them, then we call it as a transverse Doppler effect. In that situation, the apparent frequency is equals to the original frequency 1 minus v square by c square. Here it doesn't matter whether they are going away or coming closer. Reason being, we have v with the power 2. So even if it is negative, it's going to be positive. So formula will remain as it is. So let's take the first numerical. This numerical is on Michelson-Morley experiment, and what is given to us is the distance d, which is equals to 10 meter. The wavelength given is equals to 632.8 nanometer, and the orbital velocity is 3 into 10 to the power 4 meter per second. Whereas the velocity of light is 3 into 10 to the power 8 meter per second in free space. And they're asking us to find out that what is the shift when it is rotated by an angle of 90 degree. This rotation is given by the formula 2du square by c square lambda. We discussed in the previous section that this is a shift once it is rotated by an angle of 90 degree. The rest is simple. You have to put a value 2 into 10. The u comes out to be square of it, that is 9 into 10 to the power 8 divided by c, that again 9 into 10 to the power 16 multiplied by the wavelength, which is 6.328 10 to the power minus 7 meter, all in SI system. So once it is done, this comes out to be 0.32. That means there is a shift of nearly 1/3 of the fringe. This is your answer. So let's take the second numerical. This numerical is from the Galilean transformation equation. As the velocity of the moving frame is very small as compared to the velocity of light, there are two frames. One is the S frame, which is in rest, and there is a S dash frame, which is moving with velocity, let's say is Vf. And it's given that this velocity Vf, that is velocity of the frame, is 5i cap minus 5j cap plus 5k cap. And there is a particle which is initially at rest, now start moving with an acceleration a given as 2i cap plus 3j cap minus 2k cap. Remember, since acceleration remains invariant in Galilean transformation equation, so acceleration in S frame is exactly equal to the acceleration in S dash frame. But the initial position of the particle as observed by the observer O, this is R0 vector, is given, that is equals to 2i cap plus 3j plus 4k cap. Okay. With this information, let's first of all work out what is the final position at time t equals to 4. And the formula for this is r vector at 0, initial velocity multiplied by t of the particle plus half of acceleration of the particle into t square. So this position r vector is equals to r0 vector, that is given as 2i cap plus 3j cap plus 4k cap. Initial velocity is 0, so that is 0 vector, plus half of the acceleration given is, this is acceleration 2i cap plus 3j cap minus of 2k cap. If you simplify for r by putting the values, that means multiplied by t square also, whole is to be multiplied by t square, that is 16. So once you solve it, you will get the value, that is 18i plus 27j minus 12k, equation number 1. But this is for S frame, and it's asked that to find out the position in S dash frame. So for S dash frame, the position vector will be given as the position vector in S frame minus the velocity of the frame into t. So already we have calculated r. R is equals to 18i cap plus 27j cap minus 12k cap minus velocity of the frame, this was 5i minus 5j plus 5k multiplied by 4. And if you solve it, you will get the value as, this value is minus 2i cap plus 47j minus 32k. So this is the answer for the numerical number 2. Now let's take the third numerical. Third numerical is on Lorentz transformation equations for position as well as for time. What is been given to us? They have given us that in S frame the position is x equals to 5 light second. Actually it means that this is the distance, or you can say from origin to the position, the light takes 5 seconds to travel. When medium is not given to us, we take vacuum as a standard medium for it. So in fact this is 5 into 3 into 10 to the power 8 meter. You can keep this unit. So the final answer must be expressed in the light second. Now the second point, which is given that the velocity of the frame is 0.8 c and we are required to find out the position as observed from the S dash frame. So for the first part, the equation is x minus vt under root of 1 minus v square by a c square. Let's put the values here, and the time given for this is equals to 5 seconds. Time is 5 seconds, the position is 5 light second, and velocity is this. So let's put the value for x. So x here is 5 light second. I am using this unit, so I express my final answer in the same unit. So this is the velocity of light, this velocity of the frame, and we have to keep it 0.8 only, because already I have not taken the c in this case, so I should not take the c in this case too. So multiply it by 5 under root of 1 minus 0.8 whole square. Reason being, if you put 0.8 c square, they will be out, and we'll have this. So this comes out to be 4 and 5, that is 1 under root of 1 minus, this makes it 0.64, and that is equals to 1 divided by under root of 0.36, and that is equals to 1 divided by 0.6, and that comes out to be 1.67. Since I have not used c here, so I must express my answer in light second. So this is answer for the first part. You can do by taking this distance. If you take this distance, do take with this velocity v, multiplied with the velocity of light, that is 3 into 10 to the power 8, you will get the similar answer. So for the part B, where we have to get the transformation for time, t dash is given as t minus v x divided by c square under root of 1 minus v square by c square. Let's put the value. T is 5. So once again I am not using c. So this makes it 0.8, and for x it is 5. I missed c and c on the numerator. So c square will be out from here, and that is equals to under root of 1 minus 0.8 whole square. So once again this is equals to 4, 5, 1 point, this is 0.6, and your answer is 1.67 second. So this is answer for the second one. So here you have to be very careful. If you are initially decide whether you want to use the actual distance in SI system, or you want to use a new unit for distance, that is light second. It is similar to the light year, that is a distance traveled by light in 1 year. This also is a common unit. So if you are using it, please don't use or don't multiply by c here for v. Right? This you have to care to get the answer in a proper manner, or either you do everything in the SI system. That also is one of the method. So let's take the fourth question. In this question, two events are given to us. The one event, event 1, is given, that is the position 2 light second, and the time is 3 seconds. The event 2 is given 6 light second and time is 7 seconds. And we are asked to find out the space-time interval, that is in the A part. space-time interval in our case is going to be x square minus c square t square. This is the difference between the two events. If I write properly, this must be written this way, minus c square t2 minus t1 whole square. So this is equals to 6 minus 4 light second, or you can simply write this as 4c whole square minus c square t2 is 7 minus 3 whole square. So this is 16c square minus 16c square, and that comes out to be 0. So the space-time interval is 0. That means we are at the present position. And in the second part he is asking what type of the interval is this. So obviously, since s is 0, or you can say s square is 0, so this is the light-like event. That is the answer for the second part of it. If it comes out to be s square less than that of 0, this is going to be time-like, or if it is greater than, then it is space-like. So now let's take the fifth question. In this question, it is given that in S frame, which is at rest, there are two events. One occur at the position x equals to 0 and time 0, and other event occur at 5 light second and time 4 second. Now when observed from the S dash frame, which is moving along the x-axis, it is found that the event 2 occur 1 second earlier. Now we have to find out the velocity of S dash. So let's take the transformation equation for time, that is a Lorentz transformation equation, 1 minus v square by c square, and take the difference of this. That is delta t dash is equals to delta t minus v delta x divided by under root of 1 minus v square by c square. Since this second event appears to occur 1 second earlier, now if I have to take this delta t dash, which is nothing but is t2 dash minus t1 dash, that is delta t dash. So since the second event occur 1 second earlier, that means this time interval is plus 1 second. So putting the value of delta t here, 1 second is equals to delta t in this case is 4 minus 0, 4 second. Velocity is v, we don't know the velocity, but delta x is 5 light second. 5 into c divided by c square under root of 1 minus v square by c square. So one of the c is out. So let's take now v by c as p to make it simple. Now we have 1 minus 1 equals to 4 minus 5p divided by under root of 1 minus p square. So squaring and taking this on this side, this gives me 1 minus p square is equals to 16 plus 25p square minus 40p. Now readjusting, taking this minus p on that side, this gives me 26p square minus 40p and plus 15 is equals to 0 is a quadratic equation. We can solve it. If you solve it using discriminant method, you will find the value of the p comes out to be, there are two values. One is 0.89 and other is 0.647. Both are positive, so can be the candidate for the correct answer, but we have to check one thing. Let's look at this equation. If I look at this equation, which is 4 minus 5p, if I use this 0.89 here for p, obviously 5 into 0.89 will give me, that gives me 4.45, and once it is 4.454 minus, that makes it negative, and this difference is positive. So I rule out this option, that means this option is out from the scene. So we have the correct value of the P as 0.647, or we can say velocity is equals to 0.647 multiplied by 3 into 10 to the power 8 meter per second, and if you solve it, this value comes out to be 1.994 into 10 to the power 8 meter per second. So this must be the velocity of S dash frame, so that the second event appears to be earlier, 1 second earlier than the first event, as observed from the S dash frame. Now let's take the sixth numerical. In this numerical, it is given that on Earth there is a frame which is having the height 20 meter and its width is 5 meter. There is a spaceship which is moving with the velocity 0.8 c. C is the velocity of light. So he is asking that what should be the area as observed by the observer who is in this spaceship which is going with the velocity 0.8 c. Now since this distance is perpendicular to the movement, so there will be no change in this, that is the width will remain 5, width it means 5 even for the observer in S dash frame, but there is a change in the length, and length now will be the original length minus, and this now is equals to v square by c square. So this comes out to be under root of 1 minus 0.64, that is equals to under root of 0.36, or that is L0 into 0.6. So this is 20 meter multiplied by 0.6, that is equals to 12 meter, and area, if you look at this, the area will be 12 multiplied by 5, that is 60 meters square. That is the area observed by the person who is in the spaceship. Now let's take the sixth numerical. In this numerical, it is given that on Earth there is a frame which is having the height 20 meter and its width is 5 meter. There is a spaceship which is moving with the velocity 0.8 c. C is the velocity of light. So he is asking that what should be the area as observed by the observer who is in this spaceship which is going with the velocity 0.8 c. Now since this distance is perpendicular to the movement, so there will be no change in this, that is the width will remain 5, width it means 5 even for the observer in S dash frame, but there is a change in the length, and length now will be the original length minus, and this now is equals to v square by c square. So this comes out to be under root of 1 minus 0.64, that is equals to under root of 0.36, or that is L0 into 0.6. So this is 20 meter multiplied by 0.6, that is equals to 12 meter, and area, if you look at this, the area will be 12 multiplied by 5, that is 60 meters square. That is the area observed by the person who is in the spaceship. So students, let's take the 7th question now. In this question it is said that there is a meter rod. This is frame. There is a meter rod in a moving frame. This is 1 meter and it is making an angle of 45 degree. Right? And this is going with the speed of 0.8 of c. That's the velocity of light. C is the velocity of light. So we have to find out what is the length and the orientation of this rod that appears to the person in the S frame. So first of all, let's find out what is the component of this length along the x-axis as observed in the S dash frame. I am doing it for the S dash frame. So this is 1 meter multiplied by cos of 45 degree, and this equals to 1 divided by under root of 2 and is 0.707 meter. Similarly, Ly dash will also be 1 into sine of 45 degree, but sine 45 also is 1 by root 2, so is 0.707 of meter. Since this frame is going along the x-axis, so there will be the contraction of length only for the x component. That means the person in the S frame will find this length to be Lx dash under root of 1 minus v square by c square, and that is equals to 0.707 multiplied by 1 minus 0.64, and that comes out to be 0.6, and this is equals to 0.4242 meter. But there is no change as far as the y component is concerned, so that still remains 0.707 meter. So obviously the length as seen by the person in the S frame, that is equals to under root of Lx square plus Ly square, that means equals to 0.4242 whole square plus 0.707 whole square, and if you simplify it, this length comes out to be 0.824 meter. This is the part 1. But now we have to get the orientation also. So if we say that the angle with the x-axis is theta x, this is going to be Ly divided by Lx, and Ly is equals to, we just worked out, it is 0.707 and this is 0.4242, and that will give you the value for theta x as 49.68 degree. So that is the answer for the second part, that is the orientation. It is slightly appeared to be raised because initially it was 45 degree in the S dash frame. It is raised because there is a contraction in the x component of this length. Now let's take the 8th question. In 8th question, it is said that an astronaut is traveling in a spaceship which is going with a speed of 0.8 c. A person on Earth observes that this reaches at a place from here that is 8 light years away. And for this man, this spaceship is going with the velocity 0.8 c. So time observed by, or time interval observed by the observer in the S frame will be 8 light year divided by 0.8 c. Cc is out, so that is equals to 10 years. So for the person who is on Earth, we'll say that the spaceship has taken 10 years to reach there. But the person in the spaceship who is actually observing the actual time interval, he will say that this time interval t0 is equals to delta t multiplied by under root of 1 minus v square by c square. This comes from the relation of time dilation, which is equals to this one. So take this on this side, you will get the actual time, because whatever he observes, that is considered as the actual time interval. So this is 10 year, 1 minus 0.8 whole square, that is 0.64, that is 10 multiplied by 0.6, and that is equals to 6 year. So this is the answer for the question number 8. So students, let's take the 9th question now. It says that the proper mean lifetime of mu meson is 2.2 into 10 to the power 2.2 into 10 to the power minus 6 of second. Suddenly large number of the mu mesons are produced in a nuclear burst. Somewhere from these mu mesons, they are moving towards Earth, and this happened at 20 km above the Earth's surface, and they are moving with the speed which is equals to 0.99 c, right? Now find out the percentage of the mu mesons reaching the Earth, right? If they are coming with this speed, the time taken to reach the Earth is going to be 20 into 10 to the power 3 divided by the velocity, that is 0.99, that is 3 into 10 to the power 8, and if you solve it, this comes out to be 0.673 into 10 to the power minus 4 of second. So this much time is taken by them to reach the Earth. But this observation is made by the person who is on the Earth. Alright? So if you look for the time, actual time, that is a lifetime, which you can say, that is a relativistic time, that will be equal to t0 divided by under root of 1 minus 0.99 whole square, and that comes out to be 15.6 into 10 to the power minus 6 of second, right? So from this information we can make out that what is the percentage. Let's first of all find out what is the fraction that reaches here. This equals to t minus t, that is the time, relativistic time, and that is equals to, if you take the percentage wise, this is n by n0 multiplied by 100 in percentage e minus, this is t, which we have calculated, 0.673 into 10 to the power minus 4 divided by the time which actually relativistic time, that is 15.6 into 10 to the power minus 6. And if you simplify this out, you will find this ratio comes out to be 1.34%. So it means that the percentage of the mu mesons they will reach on the Earth is only 1.34%. So let's take this question number 10. It's a very classical question in which two photons are moving with the speed c towards each other. Let me say this is x-axis and this direction is positive direction. I am setting a frame of reference, say s dash, on the photon b. It means that the velocity of the frame can be written as minus c because going in the negative x direction, but the velocity of the photon a, which is going in the positive direction, is plus c. So from our transformation equation for velocity, which is vx minus v divided by 1 minus v vx by c square, we can write the vx is equals to c minus of minus c 1 minus this v, which is minus c, and vx is c divided by c square. So this makes it twice of c, and 1 plus 1, that is 2, and this comes out to be c. That means the velocity of a with respect to b is still equal to c. This is a consequence of the special theory of relativity, a postulate number 2, where it said that the velocity of light remains unchanged in any inertial frame of reference. This is the consequence of the same thing. So let's take the question number 11, and in this question it is said that from the s dash frame it is observed that a particle is moving, that is going with the velocity 0.5 c at an angle of 37 degree with the x dash axis. Let's say this is s frame and this one is s dash frame. It is said that this is going with the velocity 0.8 c, and the observer O dash observes that there is a particle which is going and making an angle of 37 degree in the x dash y dash plane, and the velocity of the particle is 0.5 c. This is the observation of O dash, and we have to calculate the magnitude and the direction of the velocity as observed by the observer of S frame. Okay, first of all, let's understand that this particular angle 37 degree is from the Pythagorean pair of 3, 4 and 5. So whenever we have to write down the cos theta and sin theta, we can easily make use of it. So if I have to write down the x component, the velocity as observed by the observer O dash in S dash frame, this is going to be 0.5 c multiplied by, this is cos of 37, cos 37 is 4 by 5, so this is 0.4 of c. Secondly, vy dash comes out to be 0.5 c multiplied by 3 by 5, that is equals to 0.3 of c. But because of the velocity transformation, which is applicable for the x component as well as for the y component, although there was no such transformation for the position coordinate, but for velocity it's there because of time, because time transformation is there. So let's write down the reverse transformation equation for the velocity, that is equals to vx dash plus v divided by 1 plus, this comes out to be 1 plus vx dash divided by c square. So from this equation we have to calculate, that is equals to 0.4 of c plus the velocity with which it is going is 0.8 c divided by 1 plus 0.4 c multiplied by vx dash. Vx dash is 0.4 c and v now is 0.8 c divided by c square. So this comes out to be 0.91 c. This is my first equation. Similarly, we can go for the y component, and the y component from the inverse transformation equation is vy dash divided by 1 plus vx dash divided by c square, and we have a factor of gamma here. And to calculate gamma, 1 divided by under root of 1 minus v square by c square, that is equals to 1 minus 0.8 square, that gives me 0.64, and that is equals to 1.6. So we can easily find it out. This will be equals to, gamma makes the 0.6 to come in the numerator, and then we have vy dash. Vy dash is 0.3 c divided by 1 plus, rest is vx component. Please keep this in mind. This is the x dash component, so this is going to be 0.8 c multiplied by 0.4 c divided by c square. Right? This is vx dash and this is vy dash. So be careful. And if you solve it, this comes out to be 0.138 c, equation number 2. So once you get the component, the magnitude can easily be obtained. The v is equals to under root of vx square plus vy square, and putting the values from equation 1 and 2 we have, this comes out to be 0.92c. 92c. That is your answer. For the component, you may take the c as 3 into 10 by 8 and multiply it also to get the numerical value. But for the direction, you can go like this. Tan of theta x, that means the angle we have taken with the x-axis. So that is going to be the y component, vy divided by vx. So vy will calculate it. This is 0.138 and this is 0.91, and from here if you calculate theta x comes out to be 8.6 degree. So these are the answers of the question number 11. So let's take the 12th question. In this question, the two frames are given, S and S dash. S dash is moving with the velocity 0.8 of c along the x-axis, and it is observed that in frame S, the particle is initially moving with the velocity, that is the initial velocity is 0.4 of c. It gains a constant acceleration, that is 4 meters per second square along x-axis. We have to calculate the acceleration of the particle as observed by the observer in frame S dash. We have to find out that what is the acceleration in the frame, that is S dash. So from the relation for the acceleration transformation, this equals to ax divided by gamma cube 1 minus v by vx divided by c square. So rest we have to put the values only. So a is given is 4 meter per second square, but gamma square, let's calculate gamma 1 by under root of 1 minus v square by c square. So putting the value of v as 0.8, this comes out to be 1 divided by 0.6. So cube of that is taken in the numerator, this becomes 0.6 cube divided by, this is 1 minus, the velocity is 0.8 c multiplied by initial velocity along x-axis, and that is vx is equals to 0.4 of c out from the scene, c square, and if you solve it, this comes out to be a acceleration in frame is 0.271 meter per second square along x dash axis. So this is the answer for the question number 12. So let's take the question number 13, and in this question number 13 it is said that there is a body of rest mass 2 into 10 to the power minus 15 kg and is moving with the velocity 0.8 c. We have to calculate its kinetic energy and de Broglie wavelength. To find out the kinetic energy, first of all, let's calculate its relativistic mass. That is equals to m0 under root of 1 minus v square by c square. m0 is 2 into 10 to the power minus 15 kg. This is 1 minus 0.8 square, that is 0.64, and this equals to 0.36. 2 divided by 0.6 into 10 to the power minus 15 kg, that is equals to 3.33 10 to the power minus 15 kg. This is your first information. Now to find out the kinetic energy Ek, we will use the relation mc square minus m0 c square, that is the relativistic mass energy relation. So it is m minus m0 into c square. So 3 minus 3 minus 2, that makes it 1.33 10 to the power minus 15, and c, that gives you 9 into 10 to the power 16 joule. And if you simplify it, this comes out to be 1.197 into 10 to the power 2 joule. This is the kinetic energy. Now to find out the de Broglie wavelength, the second part, we have to find out first of all the momentum. The momentum calculation in such questions can be done with the help of Pythagorean relation. This is mc square, this is m0 c square, and this is pc. Remember this triangle, this is a very important triangle. So from here I can write mc whole square is equals to m0 c square whole square plus p square c square. So this is p square c square obviously is equals to m square minus m0 square. You take this c4 here and divide by c square to get the momentum. So the momentum is given by this relation, so you can remove this c square. So momentum is equals to m square, that is m0 square, and if you simplify, this comes out to be 7.34 10 to the power minus 7 kg meter per second. So once the momentum is known to you, you can go for the de Broglie wavelength h, that is 6.63 10 to the power minus 34 divided by the momentum, that is 7.34 into 10 to the power minus 7, and this wavelength is now 9.0 into 10 to the power minus 28 meter. So this is the de Broglie wavelength, and this was the kinetic energy of this particle. Now let's take the question number 14. This is from the nuclear fission. In these type of the processes, small amount of the mass converts into energy, because energy and mass, they are equivalent, and we have the relation that E equals to mc square, that basically links the mass with energy. In the question it is given that a uranium 235 breaks up into two parts, and one has a mass of 92.5 atomic mass unit U, and other has a mass 139.3 U. Let me call this as M1 and this as M2. So the mass defect is the difference. The mass of the uranium which has been given to you is 235.0439 minus m1 plus m2, that is 92.5 plus 139.3 u. And if you do this, you will get this answer as 3.2439 u is equation number 1. Now it said that 1 gram of uranium goes for fission. In 1 gram uranium, the number of atoms can be taken as this equals to 1, and 1 gram, if I use the mole concept to get it, it is 6.023 10 to the power 23, but these many atoms are present in 235.0439 gram of uranium. So for this particular case, this is nearly 10 to the power 20. So the total energy released can be calculated as the energy released in 1 fission, that is 3.2439, and 1 u is equivalent to 931.5 MeV, and then multiply it with 10 to the power 20. These many nuclei, they have gone for the fission. And if I calculate this, this comes out to be 7.74 into 10 to the power 24 joule. This much of energy will be released if 1 gram of uranium disintegrate into the product as mentioned in this particular question. Now let's take the 15th question. In this question, it is said that the two spacecraft are moving directly towards each other. Say craft A and craft B, they are moving towards each other, and each with the velocity 0.8 c. A signal of frequency 6 into 10 to the power 14 Hertz is emitted from one of the craft. Calculate the frequency observed by the another craft. So we know that from the longitudinal Doppler effect, the formula is nu original 1 minus v by c divided by 1 plus v by c. But we have to take v as the relativistic velocity. And moreover, if they are approaching each other, we should treat this as negative. So let's first of all calculate the relativistic velocity. The negative sign we'll use later. To calculate the relativistic velocity, we'll use the formula that is equals to v plus vx, that is actually is negative, 1 minus vvx by c square. So this is equals to 0.8 c minus of minus 0.8 c divided by 1 minus 0.8 c into 0.8 c divided by c square. If you calculate this, this comes out to be 1.6 divided by 1.64, that means 0.976 c. This is the relativistic velocity. But since we have to use it with the negative sign as they are approaching each other, so the apparent frequency which is observed is going to be 6 into 10 to the power 14 under root of 1 plus. V negative makes this plus, that is 0.976 divided by, this is plus here, so that becomes negative, so 0.976, and if you simplify it, your frequency comes out to be 5.44 into 10 to the power 15 Hertz. So that is the apparent frequency observed by the other spacecraft when original frequency is 6 into 10 to the power 14 Hertz. Hello students, now let's take the 16th question, And in this question they said that the wavelength of H alpha line is 656.3 nanometer. From a distant star this H alpha line is observed, but that observed at 850 nanometer. And we have to calculate the velocity of the star. As we know that universe is expanding, these stars are going apart, so they are receding from each other. So for the wavelength, we have the formula, that is lambda dash here is equals to lambda alpha under root of 1 plus V by C 1 minus V by C. For wavelength it becomes just the reverse of it. Instead of negative we put a positive sign here. So this we already know that this is equals to, let me take V by C as beta and just use this relation to find out 850 for alpha in a moving star. This is 656.3, right? And that is equals to, or take the square of it, that is equals to 1 plus beta and 1 minus of beta, cross multiply, and if you solve for beta, the beta comes out to be 0.2528, which gives you the velocity as 7.59 into 10 to the power 7 meter per second. So this is the velocity of the star which is receding from us. So students, with this we close this chapter at this position. As I advised you in the earlier lecture also, that if you want to really gain from these numericals, it's better to pause the video, solve it yourself, and then compare it with the answer I am giving. And if you find any discrepancy, please give the comment also. So thanks for watching. Thanks for your time.